In a clean room in Shenzhen, a silicon wafer slides into a machine unlike the ones that dominate modern chip making. There is no giant projection lens hovering overhead, no deep ultraviolet light source costing tens of millions of dollars. No complex optical system bending light through a maze of mirrors and precision glass. Instead, a template slowly descends toward the wafer, a pressure is applied, a nanoscale pattern is physically pressed into a specially prepared material, almost like stamping a seal into wax, except the details being copied are thousands of times smaller than a human hair. Seconds later, the mold lifts away and an entire photonic chip pattern remains behind. Simple in concept, potentially revolutionary in practice, that moment may seem insignificant compared to the giant headlines surrounding AI chips, quantum computing, or advanced lithography. But according to Chinese researchers and equipment makers, this manufacturing approach could reduce the cost of certain photonic chips by as much as 90%, while eliminating the need for conventional DUV lithography in the process. And if that claim proves true, the implications stretch far beyond one factory or one type of chip, because this story isn't really about replacing a machine, it's about questioning an assumption that has guided semiconductor manufacturing for decades. What if the future isn't built by making lithography more complicated? What if, for certain chips, the breakthrough comes from making it dramatically simpler? And once you see where this technology is headed, you begin to understand why so many people inside the industry are paying attention. Let's get into it. For most of the semiconductor industry's history, progress has been defined by a single idea: make the pattern smaller. Every generation of chip-making equipment was built around that goal. More precision, more complexity, more expensive optics, and more advanced light sources. The logic seemed unshakable. If you wanted more powerful chips, you needed better lithography. And if you needed better lithography, you needed increasingly sophisticated machines capable of projecting increasingly tiny features onto silicon. That belief became so deeply embedded in the industry that entire supply chains, national policies, and multi-billion-dollar investments were built around it. Companies fought to gain access to advanced lithography tools because everyone assumed those machines represented the only path forward. And to be fair, there was good reason to think that way. Modern lithography is one of humanity's greatest engineering achievements. A state-of-the-art DUV or EUV system performs tasks so precise they border on science fiction. It manipulates light with extraordinary accuracy, aligns wafers to tolerances measured in nanometers, compensates for thermal expansion, vibration, material defects, and countless other variables that could destroy a pattern before it is even transferred. These machines aren't expensive because manufacturers are charging too much. They're expensive because building them requires solving problems that only a handful of companies on Earth can even attempt to solve. But hidden inside that success was a question very few people were asking. What happens if projecting the pattern isn't actually the best way to create it? That question sounds almost ridiculous at first. After all, modern chipmaking has spent decades perfecting projection-based lithography. Why abandon a system that works? Because sometimes the best solution isn't the one with the most engineering behind it. Sometimes the best solution is the one that removes engineering entirely. Think about printing a photograph. You can project the image onto paper using a sophisticated optical system, or you can use a stamp that already contains the pattern. If your goal is reproducing the same design over and over again, the second approach suddenly starts looking very attractive. That's the fundamental idea behind nanoimprint lithography. Instead of projecting patterns using light, engineers create a master template containing nanoscale structures. That template physically touches a specially prepared material on the wafer. Pressure is applied, the pattern transfers directly into the material, the mold lifts away, the design remains. Conceptually, it's astonishingly simple, and that simplicity is exactly why the technology has fascinated researchers for decades. if you can reliably copy nanoscale patterns using physical contact, entire layers of complexity disappear. Massive optical systems become less important. Certain exposure steps can be reduced or eliminated, and some manufacturing costs potentially fall dramatically. In theory, the economics become very attractive. The problem is that semiconductor manufacturing doesn't care about theory. It cares about reality, and reality turned out to be much harder. If you've ever applied a screen protector to a smartphone, you already understand part of the challenge. Tiny air bubbles appear where you don't want them, and dust particles create imperfections. Pressure distributes unevenly. Now imagine performing that same task at dimensions measured in billionths of a meter. Suddenly, everything becomes a problem. A particle too small for the human eye to notice can destroy a critical feature. A microscopic variation in pressure can affect pattern quality. A tiny defect on the template can be replicated again and again across multiple wafers. During separation, delicate structures can tear, stretch, or deform. What looks simple from a distance becomes extraordinarily difficult up close. That's why nanoimprint lithography spent years living mostly in research papers and laboratory demonstrations. The promise was obvious. The manufacturing reality was not. And this is where China's recent announcement becomes genuinely interesting, because the companies involved aren't claiming they've solved every semiconductor problem on Earth. They're doing something much smarter. They're targeting the specific type of chip where nanoimprint strengths align almost perfectly with the product being manufactured. Photonic chips? If you've been following this channel for a while, you know that photonic chips are becoming increasingly important. Instead of moving information entirely through electrical signals, these devices manipulate light itself. They guide photons through microscopic pathways, and they split beams and filter wavelengths, direct optical signals, and create complex structures capable of transmitting enormous amounts of information with remarkable efficiency. And unlike advanced logic processors, many photonic structures share a characteristic that makes them uniquely compatible with stamping. Repetition. Lots of repetition. A cutting-edge CPU resembles a dense city where every block looks different. Millions or billions of transistors interact in highly customized arrangements. The geometry changes constantly across the chip. Photonic devices often look different. Many contain repeating optical elements, repeating gratings, repeating waveguide structures, and repeating phased array components. In other words, they contain exactly the kind of patterns that a master template can reproduce efficiently. That's a huge distinction, because disruptive technologies rarely win by replacing everything at once. They win by finding one application where they are dramatically better, and once they succeed there, they expand. If you've ever watched a technology evolve, you've probably seen this pattern before. The first version isn't perfect. The first market isn't huge. The first customers aren't everyone. But that's not the point. The point is proving that the concept works. And according to the companies involved, that's exactly what they're attempting. And by validating full 8-inch wafer production for photonic devices, they're moving beyond small laboratory demonstrations and towards something that looks much closer to real manufacturing. Now, I want to pause here for a second, because this is one of those stories where headlines can easily outrun reality. If you enjoy these deep dives that try to separate engineering facts from hype, consider subscribing. Not because subscriptions matter more than anything else, but because there are so many fascinating technology stories getting reduced to clickbait headlines. And I think it's worth taking the time to understand what's actually happening underneath them. The other reason photonic chips matter is that demand is growing rapidly. Data centers need faster optical communication, AI clusters require enormous bandwidth between processors. Telecommunications networks continue expanding. Autonomous vehicles need advanced sensing technologies. Industrial automation increasingly relies on optical systems. Every one of those trends creates demand for photonic components, and wherever demand grows, manufacturing efficiency suddenly becomes important, very important. Imagine two companies producing similar optical devices. One relies on expensive lithography steps for every wafer. The other can replicate large portions of its design through a stamping process at substantially lower cost. Even if the performance difference is small, economics start becoming powerful. That's why the claimed cost reduction is generating attention, not because every chip suddenly becomes 90% cheaper. That interpretation would be misleading. Lithography is only one part of manufacturing. Materials still cost money, equipment still costs money, testing still costs money, packaging still costs money. But if a major process step becomes dramatically less expensive, the overall economics can shift significantly. And that's exactly what engineers across the industry are now watching, because if the manufacturing numbers hold up, this isn't just a story about one machine. It's a story about whether a simpler approach can compete against one of the most sophisticated manufacturing ecosystems ever created. And in technology, those are often the stories that end up surprising everyone. What makes this development even more interesting is that it arrives at a moment when the semiconductor industry is facing a very unusual problem. For decades, the solution to almost every manufacturing challenge was straightforward, even if it was expensive. Build a better lithography machine, build a more precise optical system, build a more advanced exposure tool. Every generation pushed further in the same direction. More complexity became the answer to everything. But complexity has a cost, not just in dollars, but in time, supply chains, maintenance, energy consumption, and manufacturing risk. Eventually, every industry reaches a point where people begin asking whether there might be a simpler path, and that is exactly what appears to be happening here. Instead of competing head-on with the most advanced lithography systems ever built, Chinese engineers may have identified a category of chips where projection itself is the unnecessary step, not because optics stopped working, but because a physical template can achieve the same goal more efficiently for specific structures. That's a subtle distinction, but it matters enormously. Revolutionary technologies often succeed not by beating the incumbent everywhere, but by finding the one place where the incumbent is overqualified. The real challenge, however, begins now. Because semiconductor history is filled with technologies that looked brilliant inside laboratories and disappointing inside factories. A factory is a ruthless environment. Customers don't pay for scientific elegance, they pay for consistency, they pay for yield, they pay for reliability. If a process works perfectly 95% of the time but fails unpredictably, and the other 5%, manufacturers quickly discover that those failures erase most of the theoretical savings. And that's why the next chapter of this story won't be decided by announcements or demonstrations. It will be decided by numbers. How many wafers can the system process each day? How many chips emerge fully functional? How long do the templates last before replacement? And how often do defects appear? How repeatable are the results across thousands of production cycles? These are the questions that determine whether an engineering breakthrough becomes a business success. And this is where things become particularly fascinating, because nano-imprint lithography's biggest weakness has always been physical contact. Contact creates opportunities for contamination. Contact creates opportunities for wear. Contact creates opportunities for defects. Yet Chinese engineers appear to be attacking those weaknesses directly through vacuum environments, advanced pressure control systems, specialized resist materials. and manufacturing methods designed specifically around large-scale replication. Whether they have solved those challenges completely remains to be seen, but the fact that they're pursuing full wafer production rather than isolated demonstrations suggests confidence that the process has matured significantly beyond where it stood a decade ago. There's a broader lesson here that extends beyond photonic chips. Sometimes entire industries become so focused on improving an existing solution that they stop asking whether the solution itself should be reconsidered. That's understandable. Expertise creates momentum. Infrastructure creates momentum. Investment creates momentum. Once billions of dollars have been committed to a particular direction, changing course becomes difficult. Yet history repeatedly shows that disruptive ideas often emerge from people willing to revisit assumptions everyone else considers settled. In this case, the assumption was that increasingly sophisticated projection systems represented the inevitable future of nanoscale manufacturing. Nanoimprint asks a different question entirely. What if copying is better than projecting? If you've made it this far, I'd love to know your perspective, not because comments help a channel grow, but because some of the smartest insights often come from people looking at the same information through completely different lenses. Do you think manufacturing simplicity eventually beats manufacturing complexity, or do you believe advanced lithography will remain dominant regardless of cost? I'm genuinely curious because reasonable people can reach very different conclusions here. The potential implications stretch far beyond LiDAR systems. Imagine large-scale optical communication components becoming substantially cheaper to manufacture. Imagine photonic interconnects inside AI data centers benefiting from lower production costs. Imagine optical sensing technologies expanding into applications that previously couldn't justify the economics. None of these outcomes are guaranteed, but they illustrate why engineers are paying attention. Manufacturing breakthroughs don't always change products directly. Sometimes they change economics first, and economics often determines which technologies achieve widespread adoption. One of the most overlooked realities in technology is that cost reductions can be just as transformative as performance improvements. The world tends to celebrate faster processors, larger models, and more powerful systems. Yet many of history's biggest technological shifts happened because something became affordable enough to deploy everywhere. The internet didn't transform society because networking technology suddenly became perfect. It transformed society because costs fell far enough for adoption to explode, and the same pattern appears repeatedly across industries. Lower manufacturing costs create larger markets attract more investment accelerates innovation, innovation drives further cost reductions, the cycle feeds itself. That's why the claimed 90% reduction matters, even if the real-world number ultimately proves smaller. Whether the final savings are 90%, 50%, or even 30%, the principle remains significant. If certain photonic devices become substantially cheaper to manufacture, entirely new opportunities emerge. Products that previously sat on the edge of commercial viability suddenly become practical. Companies that hesitated to adopt optical solutions may reconsider, engineers gain more freedom to experiment, markets expand. At the same time, caution is warranted. The semiconductor industry has a remarkable ability to humble ambitious predictions, yield problems appear unexpectedly, and reliability issues emerge months later. Manufacturing bottlenecks reveal themselves only under full production conditions. Many promising technologies discover that scaling is harder than inventing. That's why I think the most honest interpretation of this announcement is neither blind optimism nor dismissal. It's curiosity. A potentially important manufacturing approach appears to be crossing from laboratory research into industrial validation. That's worth paying attention to. But the ultimate verdict will come from factories, customers, and production data rather than press releases. Personally, what I find most compelling isn't the machine itself. It's the philosophy behind it. For years, semiconductor progress has largely meant building more complicated systems to solve increasingly difficult problems. And here we have a technology attempting something almost counterintuitive. Instead of adding complexity, it's removing it. Instead of projecting a pattern through sophisticated optics, it's physically replicating it. Instead of making the process more elaborate, it's asking whether direct copying can accomplish the same result. Sometimes those kinds of questions lead nowhere. Sometimes they change industries. And that brings us back to the title of this video. The reason this story matters isn't because China has replaced DUV lithography. It hasn't. The reason it matters is because Chinese engineers may have found a category of chips where DUV isn't necessary in the first place. That's a very different claim. And in many ways, it's the more interesting one, because technological disruption rarely arrives by defeating the incumbent on its strongest ground. It arrives by changing the rules of the competition. Before we wrap up, I'd like to ask one final question. Do you think the future of photonic chips belongs to increasingly advanced lithography systems, or do you believe manufacturing techniques like nanoimprint will eventually become the preferred approach for large-scale optical devices? Share your thoughts below. I genuinely enjoy reading the discussions because these conversations often reveal perspectives I hadn't considered myself. And if you enjoy exploring the engineering, materials, and manufacturing breakthroughs shaping the future of technology, consider subscribing and joining us for future deep dives, not